Look up at the night sky. What do you see? Twinkling stars, distant planets, maybe the glow of the Milky Way stretching across the darkness. But what if I told you there's an invisible ocean of energy flooding the cosmos? A sea of light so powerful it could vaporize entire worlds, yet completely hidden from our eyes. This is the cosmic gamma-ray background, an enigmatic tapestry of high-energy radiation woven into the fabric of space itself. For decades, astronomers have known it exists, but its origins remain one of the greatest unsolved puzzles in modern science. Imagine standing at the edge of an endless, invisible storm, a storm that crackles with the energy of exploding stars, colliding galaxies, and perhaps even stranger phenomena we can't yet comprehend. That's the mystery we're diving into today. Scientists first detected this ghostly glow in the 1960s, and since then it's only grown more baffling. The gamma-ray background isn't just a faint hum, it's a roaring chorus of the universe's most violent events, each photon packing 1,000,000 times more energy than the light we see with our eyes. But here's the twist: when researchers try to pinpoint where all this energy comes from, the math doesn't add up. The brightest known sources, black holes, supernova, pulsars, account for barely half of what we observe. The rest, a total enigma. Some theories whisper of dark matter particles annihilating in the void. Others suggest undiscovered realms of physics lurking just beyond our grasp. One thing's certain: the answers we're chasing could rewrite everything we know about the cosmos. This video is your guide to the 25 deepest mysteries hiding within that gamma-ray fog. We'll journey from the hearts of distant galaxies to the quantum flickers of empty space itself, uncovering clues that could reveal the universe's best-kept secrets. Along the way, you'll meet the brilliant minds racing to solve these puzzles, and the mind-bending possibilities that emerge when we stare into the unknown. So buckle up, because by the time we're done, you'll never look at the night sky the same way again. The invisible universe is calling. Are you ready to listen? At the heart of this cosmic puzzle lies something called diffuse gamma rays, not the concentrated bursts from exploding stars or spinning neutron stars, but a faint, almost uniform glow that stretches across the entire sky. Picture it like static on an old television set, a grainy, omnipresent buzz with no obvious source. That's what astronomers see when they map the gamma-ray sky, and it defies everything we thought we knew about how the universe produces high-energy light. The strangest part: these gamma rays aren't just floating randomly. They cluster in ways that hint at hidden structures, vast, invisible rivers of energy weaving through the cosmos. Some regions shine brighter, others dimmer, like a fingerprint smudged across the heavens. Early theories assumed they were just the combined glow of countless distant galaxies, each contributing a minuscule flicker. But when scientists added up all the known gamma-ray sources, every black hole jet, every supernova remnant, they barely scratched the surface of what's actually out there. The numbers fell staggeringly short. What's even more baffling is how these diffuse rays behave. Unlike gamma rays from identifiable objects, which often spike and fade, this background hum remains eerily steady. It's as if the universe itself is humming a tune we can't quite place. Some researchers speculate it could be the collective whisper of dark matter particles colliding and annihilating in the void. Others think we might be seeing the echoes of primordial cosmic events, relics from a time when the universe was young and seething with unimaginable energy. Then there's the Fermi Bubbles, two colossal gamma-ray-filled structures ballooning from the Milky Way's core. Discovered just over a decade ago, these enormous lobes stretch 25,000 light-years into space, crackling with energy no known process can fully explain. Are they the remnants of an ancient galactic eruption, a sign of our supermassive black holes past tantrums, or something even more exotic? Whatever they are, they're a stark reminder that the diffuse glow we see isn't just background noise, it's a story waiting to be decoded. Every time astronomers think they're close to an answer, the gamma-ray sky throws another curveball. Take the so-called Fermi haze, a mysterious fog of high-energy particles enveloping the galaxy's center. Or the way certain patches of diffuse light align with galaxy clusters, as if some unseen force is funneling energy through the cosmic web. Even after decades of study, the origin of these rays remains one of astrophysics' most stubborn enigmas. And that's what makes this mystery so thrilling, because somewhere in that invisible glow could be clues to forces we haven't even dreamed of yet. Blazars should be the universe's flashlight, supercharged beacons capable of lighting up the entire cosmos with gamma rays. These monstrous objects are essentially supermassive black holes at the centers of distant galaxies, devouring matter and firing jets of radiation so intense they can outshine every star in their host galaxies combined. With that kind of power, you'd think they'd dominate the gamma-ray background, plastering the sky with their unmistakable glow. But here's the catch: when scientists tally up all the blazars we've detected, their combined output barely makes a dent in the mysterious sea of gamma rays we observe. It's like expecting a roaring bonfire and finding only a handful of scattered matches. The discrepancy is staggering. Blazars are so bright individually that for years astronomers assumed they were the primary architects of the diffuse gamma-ray background. Yet when the Fermi Gamma-Ray Space Telescope mapped the sky with unprecedented precision, the numbers told a different story. Even after accounting for every known blazar, every jet, every flare, their total contribution amounts to less than a third of the background's intensity. That leaves a gaping hole in our understanding. Where is the rest coming from? One possibility is that we're missing countless faint blazars lurking just beyond our detection threshold. Think of it like trying to count fireflies in a foggy field. You might spot the brightest ones, but the weaker glimmers blend into the haze. Some models suggest these hidden blazars could be peppering the universe in vast numbers, their collective faintness masking their true influence. But even if that's the case, simulations show they'd still fall short of explaining the background's full intensity. The math stubbornly refuses to balance. Then there's the question of time. Blazars are notoriously erratic, flickering like cosmic strobe lights as their black holes gulp down matter in fits and starts. Yet the gamma-ray background remains eerily steady, a constant hum rather than an erratic symphony. If blazars were the main contributors, we'd expect their variability to imprint itself on the background, creating ripples of fluctuation. Instead, the signal is smooth, almost too perfect, as if something far more subtle and pervasive is at work. This isn't just a bookkeeping error in astrophysics. The missing blazar problem forces us to confront an unsettling truth. Our catalogue of the universe's most extreme objects is incomplete. Could there be an entirely new class of gamma-ray emitters hiding in plain sight? Some theorists speculate about exotic phenomena, like decaying dark matter or primordial black holes evaporating into bursts of energy. Others wonder if we're seeing the cumulative effect of countless smaller, overlooked sources, cosmic fireworks too faint or diffuse to spot individually. The deeper we dig, the stranger it gets. Recent studies have even found that blazars' gamma rays don't distribute evenly across the sky. They cluster in ways that suggest large-scale structures, filaments of galaxies or dark matter halos, might be magnifying their light like a cosmic lens. If true, it would mean the universe itself is warping and amplifying these signals in ways we're only beginning to grasp. But even that can't fully bridge the gap between what blazars produce and what we actually see. What's clear is that the gamma-ray background isn't just a backdrop, it's a mirror reflecting our ignorance. Every photon we can't trace to a known source is a clue pointing to undiscovered physics, to forces and objects lurking beyond the edge of our current maps. And until we solve the riddle of the missing blazars, we're left staring into the dark, knowing the cosmos still has cards it hasn't revealed. Star-forming galaxies should be brimming with gamma rays. After all, they're cosmic factories churning out massive stars that live fast and die violently. When these stars explode as supernova, they unleash shockwaves powerful enough to accelerate particles to near light speeds, creating gamma rays in the process. With billions of such galaxies scattered across the universe, it's tempting to think they could be the missing piece of the gamma ray background puzzle. But when astronomers crunch the numbers, they hit the same frustrating wall. Even the combined might of these starry dynamos falls far short of explaining the relentless glow filling the cosmos. Take the Milky Way's neighbor, the Andromeda Galaxy. It's a bustling hub of star birth with hundreds of new stars igniting every year. Yet when scientists measured its gamma ray output, it was a mere flicker compared to the background's intensity. Scale that up to every star-forming galaxy in the observable universe, and the total still leaves a yawning gap. Why? Because most of the energy from these galaxies gets soaked up by their own gas and dust before it can escape into intergalactic space. It's like trying to light up a football stadium with a handful of glow sticks. Each one shines bright up close, but their collective glow barely pierces the darkness. There's another twist. Star-forming galaxies don't emit gamma rays evenly. Their output depends on how frenetically they're birthing stars, and that activity fluctuates over cosmic time. Billions of years ago, when the universe was younger and denser, galaxies were churning out stars at a breakneck pace. Back then, their combined gamma ray glow might have been far brighter. Yet even when scientists model this peak era of star formation, the numbers still don't align with the smooth, unchanging background we see today. If these galaxies were the primary source, we'd expect the gamma ray fog to vary with distance older, fainter light from the early universe blending with younger, brighter emissions from closer galaxies. Instead, the signal is eerily uniform, as if something else is fine-tuning the balance. Some researchers argue we might be underestimating a hidden population of dwarf star-forming galaxies, tiny, faint systems too dim for current telescopes to spot. These cosmic minnows could be flooding the universe with gamma rays, their sheer numbers making up for their individual weakness. But here's the catch. Even if they exist in vast quantities, their gas-rich environments would trap much of that radiation before it could leak into deep space. It's a cosmic catch-22. The galaxies most likely to produce gamma rays are also the ones best at muffling them. Then there's the role of cosmic rays, high-energy particles that slam into gas clouds within galaxies, generating gamma rays as collateral damage. In star-forming galaxies, these collisions should be constant, like a never-ending hailstorm. But recent observations reveal something odd. The gamma rays we detect often don't match the expected patterns of cosmic ray interactions. Some regions glow too brightly, others remain suspiciously dark. This mismatch hints that another process may be something exotic, like dark matter decay or even quantum foam fluctuations, could be muddying the waters. The more we study star-forming galaxies, the clearer it becomes. They're part of the story, but not the whole story. Like blazars, they're pieces of a puzzle that refuses to snap neatly into place. And that's what makes this mystery so tantalizing. Because if even the universe's most prolific energy factories can't account for the gamma ray background, what unseen engines are humming in the shadows? Could there be an entirely new class of objects, dim, diffuse, or so strange we haven't even imagined them yet, pumping out this elusive light? The answer might lie not in the galaxies we see, but in the darkness between them. What if the answers to the gamma ray background puzzle aren't hiding in the light, but in the dark? For decades, scientists have suspected that dark matter, the invisible glue holding galaxies together, might be silently leaking gamma rays into the cosmos. This isn't just wild speculation. If dark matter consists of certain theoretical particles, their collisions or decays could produce bursts of high-energy light, stitching faint threads into the gamma ray tapestry we observe. It's a hypothesis as elegant as it is elusive, dancing at the edge of discovery without ever quite stepping into the light. The logic is compelling. dark matter outweighs ordinary matter 5 to 1, meaning its potential energy reservoir dwarfs everything stars and galaxies could ever produce. Certain models, like those involving weakly interacting massive particles, WIMP, predict these particles could annihilate when they collide, converting their mass into gamma rays. Picture it like invisible stars burning in reverse. Instead of fusing atoms to create light, they'd vanish in flashes of pure energy. In regions where dark matter clumps densely, like the cores of galaxies or vast halos enveloping galaxy clusters, these annihilations could generate just the kind of diffuse glow we detect. But here's the catch: no one's ever seen it happen. Despite scanning the skies with instruments like the Fermi telescope, the telltale gamma-ray signatures of dark matter remain stubbornly absent. Or do they? Some researchers point to curious excesses of gamma rays emanating from the Milky Way center, where dark matter should cluster most densely. These signals align roughly with what WIMP annihilations might look like, but they also overlap with other messy astrophysical processes like pulsars or gas clouds bombarded by cosmic rays. It's like trying to hear a whisper in a windstorm. The signal blurs into the noise. The debate grows even thornier when you consider alternative dark matter candidates. Actions, sterile neutrinos, or even primordial black holes could decay or interact in ways that produce gamma rays, but each theory leaves its own distinct fingerprint. If actions decay, for example, they'd emit gamma rays at very specific energies, creating spectral lines we could hunt for. So far, no such lines have been conclusively spotted. Meanwhile, simulations of dark matter halos suggest their gamma-ray emissions should trace the intricate webs of cosmic structure, yet the real gamma-ray background appears smoother than the models predict. Perhaps the most tantalizing clue comes from dwarf galaxies. These faint, dark matter-dominated satellites of the Milky Way should be pristine laboratories for dark matter signals, with minimal interference from ordinary astrophysics. Yet when scientists scrutinized them, the gamma-ray harvest was meager. Some dwarfs showed faint excesses, others nothing at all. It's as if the universe is teasing us with half-answers, dangling possibilities just out of reach. The frustration is palpable, but so is the promise. If dark matter is indeed the source of even a fraction of the gamma-ray background, it would revolutionize particle physics and cosmology overnight. We'd finally have a window into the invisible 85% of the universe's matter, unlocking secrets hidden since the Big Bang. Until then, the hunt continues with ever more sensitive detectors and sharper theoretical tools probing the darkness. One thing's certain: whether dark matter's fingerprints are there or not, the search itself is revealing just how much we still have to learn about the universe's shadowy side. Among the gamma-ray background's many riddles, few are as perplexing as the unexplained high-energy peaks, sudden, sharp spikes in the spectrum where no known astrophysical process should produce them. These aren't just minor blips in the data. They're like cosmic screams at energies so extreme they defy even the most violent events we've catalogued. Imagine listening to a symphony and hearing a note so piercing it shatters the orchestra's instruments. That's the kind of anomaly astronomers are up against. The first clues emerged when space telescopes like Fermi and the High-Energy Stereoscopic System, HESS, began mapping the gamma-ray sky in ultra-high resolution. Nestled within the smooth haze of the background, they spotted narrow, intense bands of light at specific energies, some exceeding 1 trillion electron volts. To put that in perspective, that's 1 million times more energetic than the X-rays used in hospitals, packed into a single photon, the strangest part. These peaks don't match the expected signatures of any known particle or process. Not blazar jets, not pulsar winds, not even the shock waves of supernova. They're spectral outliers, like finding a fingerprint at a crime scene that doesn't belong to any known species. One leading theory points to dark matter specifically, the possibility that certain dark matter particles, when they collide or decay, could release gamma rays at very precise energies. It's a tantalizing idea, like finding a smoke signal from the universe's most elusive substance. If true, these peaks would be the smoking gun physicists have hunted for decades. But there's a catch. The observed energies don't neatly align with most popular dark matter models. The numbers are off sometimes by just enough to keep theorists awake at night, scribbling equations in the margins. Then there's the puzzle of location. These high-energy peaks aren't scattered randomly. Some cluster near regions where galaxies pile up in dense filaments, or around mysterious voids where the cosmic web stretches thin. A few even seem to trace the edges of ancient supernova remnants, like echoes of long-dead stars. But here's the twist: no single explanation fits all the data. Some peaks appear where dark matter should dominate, others flare in areas teeming with ordinary matter. It's as if the universe is playing a game of peekaboo, alternating between different sets of rules. Could these peaks be the work of something even stranger? Quantum gravity effects, extra dimensions, or primordial black holes evaporating in bursts of Hawking radiation have all been floated as wildcards. One hypothesis suggests that space-time itself might be frothing with tiny, ephemeral bubbles at the quantum scale, and their collapse could release gamma-ray flashes at ultra-high energies. It sounds like science fiction until you realize these ideas are the cutting edge of what's mathematically possible. The stakes couldn't be higher. If these peaks stem from new physics, they could rewrite the standard model of particle physics. If they're artifacts of unknown cosmic cataclysms, they might reveal entirely new classes of astrophysical objects. And if they're simply noise, some quirk of instrumentation or statistical fluke, then we're back to square one, staring at a sky full of questions. For now, the peaks remain a cosmic cipher, encrypted in light we're still learning to read. Every new observation brings us closer to cracking the code, but the universe, as always, guards its secrets fiercely. Rising from the heart of our galaxy like two colossal hourglasses, the Fermi Bubbles defy every expectation. These towering structures, each stretching 25,000 light-years from the Milky Way's core, glow with gamma rays so intense they outshine the rest of the galactic plane. Discovered in 2010 by the Fermi Gamma Ray Space Telescope, they're not just another cosmic curiosity. They're a blistering anomaly etched across the sky, challenging our understanding of how galaxies distribute energy. What makes these bubbles so baffling isn't just their size, it's their sheer audacity. They shouldn't exist under conventional models of galactic physics. Imagine blowing smoke rings the height of Mount Everest, only these rings are made of pure radiation and stretch halfway to the edge of the galaxy. The energy required to create them is staggering, equivalent to 100,000 supernova detonating in unison. Yet there's no record of such an apocalyptic event in our cosmic backyard. No ancient cataclysm, no visible scars, just these silent, shimmering giants looming over us. The leading theory suggests our supermassive black hole, Sagittarius A, might have erupted in a violent outburst millions of years ago, spewing jets of high-energy particles that inflated the bubbles like cosmic balloons. But here's the catch: the bubbles' gamma rays don't match the expected signature of black hole jets. Instead of the focused beams we see from active galaxies, the Fermi bubbles emit a diffuse, almost uniform glow, as if their energy has been stirred and smeared by unseen forces. Some researchers propose colossal magnetic fields might be shaping them, while others wonder if dark matter annihilations near the galactic center could be fueling their glow. Even stranger is their relationship to the broader gamma-ray background. While the bubbles contribute a significant fraction of the Milky Way's high-energy light, their emissions are oddly disconnected from the smooth, all-sky haze astronomers observe. They're like two bonfires in a foggy field, bright and localized, yet somehow separate from the mist. This disconnect hints that whatever mechanism sculpted the bubbles might also be operating on a far grander scale, hidden in the universe's darkest corners. Then there's the mystery of their edges. Unlike most galactic structures which fade gradually into the void, the Fermi bubbles have razor-sharp boundaries, as if confined by an invisible barrier. Simulations struggle to replicate this crispness. Cosmic gas and magnetic fields should blur their outlines over time. One provocative idea suggests shockwaves from the original eruption might still be propagating, compressing the bubble's walls like a cosmic pressure cooker. Others speculate that dark matter filaments threading through the galaxy could be acting as scaffolding, pinning the bubbles in place. The most tantalizing clue lies in their symmetry. Perfectly aligned with the galactic center and mirroring each other almost flawlessly, the bubbles suggest a single, catastrophic injection of energy. Yet when astronomers scrutinize the Milky Way's quieter neighbor, Andromeda, they find no similar structures. If black hole outbursts are common, why don't all galaxies sport these gamma-ray halos? The answer might lie in timing. Perhaps the bubbles are relics of a rare, hyperactive phase in Sagittarius A's life, a feeding frenzy we just happen to catch the aftermath of. Every new observation deepens the intrigue. Recent studies have detected faint X-ray counterparts to the bubbles, along with subtle distortions in their shapes that hint at past interactions with galactic winds. Even more perplexing, some gamma rays within the bubbles appear slightly more energetic than expected, as if an unseen accelerator is still cranking particles to extreme speeds. Whether these are echoes of the original eruption or signs of ongoing activity, one thing's clear: the Fermi bubbles aren't just ghosts of the past, they're alive with secrets, and their story is still being written. Solving their riddle could rewrite galactic physics. If the bubbles stem from black hole activity, they'd prove even dormant giants like Sagittarius can reshape entire galaxies in moments of fury. If dark matter is involved, they might be our first tangible glimpse of its interactions. And if there's something entirely new, well, that's the thrill of the hunt. For now, these silent sentinels stand as a reminder that sometimes the most profound mysteries aren't in the distant cosmos, they're right over our heads, glowing faintly in light we're only beginning to decipher. Gamma rays don't travel through the universe alone, they're constantly tangoing with an invisible partner known as the extragalactic background light, or EBL. This faint glow, a patchwork of starlight and dust emissions accumulated over billions of years, fills every corner of space like a cosmic fog. And here's where things get tricky. When high-energy gamma rays collide with these low-energy EBL photons, they can annihilate each other in a spectacular subatomic duel, transforming into pairs of particles and effectively dimming the gamma ray signal we detect. It's a process so predictable in theory that scientists use it as a measuring stick to map the universe's structure. But when astronomers compare predictions to observations, the numbers don't just disagree, they tell two entirely different stories. Take a gamma ray fired from a blazar halfway across the universe. By the time it reaches us, its journey should leave a telltale imprint of energy loss, like a marathon runner crossing the finish line exhausted, their speed sapped by every mile traveled. The farther the blazar, the more EBL interactions should erode its gamma rays, creating a clear pattern where distant sources appear dimmer than nearby ones. Except they don't. Some of these far-flung gamma rays arrive suspiciously intact, punching through the EBL fog as if it weren't there. It's the equivalent of a runner showing up fresh as a daisy after a 100-mile sprint, leaving physicists scrambling for explanations. One possibility is that our models of the EBL itself are flawed. Maybe the universe's fog bank is thinner or patchier than we've assumed. But when astronomers cross-check with infrared and optical surveys, the tools that directly measure EBL density, the observations line up neatly with expectations. The fog is right where it should be, just as dense as predicted. So why aren't the gamma rays obeying the rules? Then there's the quantum wildcard, photon mixing. Some theories suggest gamma rays might morph into hypothetical particles called actions mid-journey, slipping past EBL photons unnoticed before reverting to their original form closer to home. It's a cosmic sleight of hand that could explain the two bright signals, but it hinges on physics beyond the standard model, requiring particles nobody's ever detected. Others propose that gamma rays are finding shortcuts through space-time itself, warping around the EBL in ways we can't yet model. The plot thickens when you examine specific energy ranges. Certain gamma rays, those at the very highest energies, seem to interact with the EBL exactly as predicted, while mid-range photons defy the rules entirely. This bizarre selectivity implies there might be multiple mechanisms at play, some understood and others utterly mysterious. Imagine throwing a handful of marbles at a mesh screen. Most bounce off, but a few inexplicably pass through untouched. That's the level of strangeness we're dealing with. What's at stake isn't just a tweak to astrophysical equations. If gamma rays really are evading the EBL through unknown processes, it could mean our entire framework for understanding the universe's transparency, or lack thereof, is incomplete. Are we missing a fundamental property of light itself, misjudging the expansion history of the cosmos, or glimpsing the first hints of physics that operate beyond our current theories? Every anomalous gamma ray carries a clue, and as detectors grow more sensitive, the EBL puzzle may yet reveal secrets hidden in plain sight. Gamma ray astronomy operates on a simple premise: if you can't explain something, you haven't found all the pieces yet. That logic hits a wall when confronting the missing point source's countless pinpricks of high-energy light that should exist but remain stubbornly invisible. The math is brutally clear. When you subtract all the known gamma-ray emitters, blazars, pulsars, supernova remnants from the total background, a whopping 40% of the signal has no identifiable origin. It's like hearing a symphony where half the instruments are playing from behind a curtain. This isn't just a case of dim objects hiding in the noise. Modern telescopes like Fermi and the upcoming Cherenkov telescope array can spot gamma-ray sources fainter than ever before, yet the gap persists. The unresolved fraction behaves unlike any catalogued objects. It's too smooth, too evenly distributed across the sky. Known point sources cluster along the galactic plane or in distant galaxy clusters, but this missing component lingers everywhere, as if woven into the fabric of space itself. Some researchers argue we're seeing the collective glow of trillions of faint sources, each too weak to detect individually. Imagine trying to count every raindrop in a thunderstorm by catching them one at a time. The sheer scale might render them invisible to our tools. Alternative explanations border on the surreal. One radical proposal suggests that space-time could be frothing with quantum-scale black holes left over from the Big Bang, each evaporating in a final burst of gamma rays. Another posits that cosmic strings, hypothetical defects in the universe's structure, might be vibrating like snapped guitar strings, releasing energy as they fray. Even more unsettling is the possibility that we're seeing the cumulative flicker of alien civilizations harnessing unimaginable energies, though most scientists consider that a last resort hypothesis. The real frustration lies in the energy spectrum of these missing sources. Their gamma rays skew toward lower energies, unlike the extreme photons from blazars or neutron stars. This soft signature points to quieter, more mundane processes, perhaps vast populations of pulsars too old to emit the characteristic lighthouse beams we associate with them, or rogue planets colliding in the voids between stars. Yet when astronomers simulate these scenarios, they still fall short of the observed background's intensity. What makes this mystery particularly galling is its kinship with other cosmic puzzles. The same missing point source problem plagues X-ray and radio astronomy, suggesting a universal blind spot in how we trace energy across the spectrum. Some theorists whisper of a dark sector of physics, particles or forces that interact only weakly with ordinary matter, producing gamma rays as a rare byproduct. If true, these shadowy processes could be painting the sky with light we're only now learning to decode. Time and technology may tilt the scales. next-generation observatories promise to peer deeper into the gamma-ray fog, hunting for the faintest contributors. But until then, the unresolved background stands as both a monument to our ignorance and a beacon for discovery, because in the gaps between what we see and what we expect lies the frontier where new physics waits. Cosmic rays and gamma rays seem like they should be partners in crime, two sides of the same high-energy coin. After all, cosmic rays are fast-moving particles, mostly protons, screaming through space at nearly the speed of light. When these particles slam into gas clouds or magnetic fields, they can produce gamma rays as a byproduct, like sparks flying from a grinding wheel. Logically, this process should account for a hefty chunk of the gamma ray background. But when scientists follow the trail, they hit a roadblock. The numbers just don't add up. Take our own galaxy as an example. The Milky Way crackles with cosmic rays accelerated by supernova shockwaves and twisted magnetic fields. These particles constantly collide with interstellar gas, creating gamma rays in a process called hadronic interaction. It's a well-studied phenomenon, and in regions like the galactic plane, it explains a significant portion of localized gamma ray emissions. Yet when astronomers scale this up to the entire universe, adding contributions from all galaxies and the vast spaces between them, the total gamma ray output falls far short of the diffuse background we observe. It's as if we're trying to fill an Olympic-sized pool with water from a garden hose. The disconnect grows even wider when you examine the energy spectrum. Cosmic ray interactions tend to produce gamma rays in a predictable range, with a distinct cutoff at higher energies. But the gamma ray background doesn't play by those rules. It extends smoothly into realms where cosmic rays alone can't take the blame, suggesting another mechanism, or perhaps many mechanisms, must be at work. Some researchers point to unresolved populations of cosmic ray accelerators, like hidden supernova remnants or rogue stars flinging off particle winds. Others speculate about exotic processes like decaying dark matter or even quantum anomalies in the fabric of space itself. Then there's the puzzle of distribution. Cosmic rays are notoriously messy travelers, zigzagging through magnetic fields in erratic paths. By the time they interact to produce gamma rays, their origins are often lost in the chaos. Yet the gamma-ray background is eerily uniform, lacking the clumpy, irregular patterns you'd expect from such stochastic processes. It's like hearing a perfectly tuned chord from an orchestra playing out of sync. Something doesn't compute. Perhaps the most tantalizing clue comes from galaxy clusters, the universe's largest structures. These cosmic metropolises should be teeming with gamma rays from trapped cosmic rays colliding with cluster gas. But when telescopes like Fermi take a closer look, the signals are fainter than predicted, as if some invisible hand is dimming the lights. One theory suggests that magnetic fields within clusters might be suppressing gamma-ray production, scattering cosmic rays before they can interact. Another posits that we're underestimating how efficiently these environments absorb high-energy photons, effectively hiding them from view. The cosmic ray gamma ray link isn't just a dead end, it's a signpost pointing to gaps in our understanding. If cosmic rays were the sole architects of the gamma ray background, we'd expect a much noisier, more uneven sky. Instead, we're left with a smooth, pervasive glow that defies simple explanations. Whether the missing pieces involve unknown astrophysical accelerators, new physics, or something stranger still, one thing's clear: the universe's high-energy ledger hasn't been balanced yet. And until we crack this cosmic accounting problem, the gamma-ray background will keep its secrets locked away. Supernova remnants should be gamma-ray powerhouses after all. They're the aftermath of the universe's most violent stellar explosions, where shockwaves rip through space at thousands of kilometers per second, accelerating particles to mind-bending energies. These chaotic debris fields are essentially natural particle colliders, cranking out gamma rays as cosmic rays smash into surrounding gas and dust. With millions of such remnants scattered across the cosmos, it's easy to assume they're major players in the gamma-ray background. Yet when astronomers tally up their contributions, the numbers tell a frustrating story. Even the most energetic remnants barely make a dent in the cosmic glow we observe. Consider the Crab Nebula, one of the brightest supernova remnants in the sky. Its pulsar, a spinning neutron star, blasts out a relentless wind of high-energy particles, lighting up the surrounding wreckage with gamma rays. But here's the catch. The Crab's emissions are concentrated and localized like a spotlight in a dark room. Scale that up to all known remnants, and their combined output is a drop in the bucket compared to the diffuse all-sky background. Why? Because most remnants fade quickly, their shockwaves losing steam as they plow into interstellar space. Within a few tens of thousands of years, a blink in cosmic time, they stop producing significant gamma rays, leaving vast stretches of the universe's history unaccounted for. The timing problem runs even deeper. Supernova activity wasn't constant across the ages. It peaked billions of years ago when the universe was younger and stars formed at a frenzied pace. Back then, the collective gamma-ray glow from remnants should have been far brighter. Yet the background we see today is remarkably uniform, with no telltale dip or surge betraying that explosive past. It's as if the universe hit a cosmic mute button, smoothing out the echoes of these cataclysms into a steady hum. Some theorists argue that older remnants might still contribute indirectly, their decaying shockwaves seeding the interstellar medium with particles that later produce gamma rays. But simulations show this secondary process is too weak to explain the background's intensity. Then there's the energy mismatch. Supernova remnants excel at generating gamma rays in the mid-range energies, but the background spectrum stretches far beyond their limits. The highest energy photons, those packing trillions of electron volts, require accelerators far more powerful than even the mightiest stellar explosions. This suggests something else. Perhaps supermassive black holes or dark matter annihilations must be filling the gap. Even more puzzling is the spatial distribution. Remnants tend to cluster along the Milky Way's spiral arms, where star formation is most active. But the gamma-ray background blankets the entire sky, including the voids between galaxies where supernovae are rare. If remnants were the primary source, we'd expect a patchy, uneven glow, brighter along galactic plains and fainter in the deserts of intergalactic space. Instead, the signal is eerily homogeneous, as if something beyond individual galaxies is orchestrating the light. Could we be missing a hidden population of remnants? Some might be too faint or too distant for current telescopes to spot. Others could be embedded in dense gas clouds, their gamma rays absorbed before they escape. But even if these unseen contributors exist, they'd need to outnumber known remnants by orders of magnitude to tip the scales, a scenario that strains credibility. The truth is, supernova remnants are spectacular local phenomena, but they're not the universe's gamma-ray workhorses. Their limitations point to a broader truth. The cosmic background isn't just the sum of familiar objects. It's a tapestry woven from threads we're still learning to see, some from the darkest corners of space, others from realms of physics we've yet to uncover. And that's what makes this mystery so thrilling, because every time we rule out a known source, we're one step closer to discovering something entirely new. Long before galaxies took shape, when the universe was a seething cauldron of raw energy, something strange left its mark on the gamma-ray background. This ancient light holds whispers from the cosmos' first chapters, a time so violent and alien that even black holes were newborns. The prevailing theory suggests that in those early moments, voracious quasars and collapsing proto-galaxies flooded space with high-energy photons, creating a primordial fog that never fully dissipated. But here's the puzzle. When we run the numbers, these baby universe gamma rays shouldn't still be hanging around in the quantities we detect today. Picture the early cosmos as a pressure cooker. Matter was packed so densely that any gamma rays produced would have immediately collided with electrons and protons, getting absorbed and re-emitted countless times before finally breaking free during the universe's clearance sale. That pivotal moment 380,000 years after the Big Bang, when atoms formed and light could travel unimpeded. Yet the gamma-ray background we see now carries spectral fingerprints suggesting some of these photons slipped through the chaos unscathed, like survivors of a cosmic war. How one radical idea points to cosmic inflation, that brief period when the universe expanded faster than light itself. If inflation stretched some early gamma rays to lower energies before the particle soup thickened, they might have avoided annihilation, preserving a ghostly afterimage of the universe's birth pangs. It's like finding a perfectly preserved snowflake in a blast furnace. The odds seem impossible, yet the evidence lingers. Then there's the dark matter angle. If certain exotic particles decayed en masse during the universe's first second, they could have flooded space with gamma rays that cooled along with the expanding cosmos. These relics would now blend seamlessly into the background, indistinguishable from younger emissions except through their subtle energy distribution. Tantalizingly, some models show this could account for up to 20% of the modern gamma-ray fog, if we're interpreting the faint spectral clues correctly. The most mind-bending possibility involves quantum gravity effects. In the Planck epoch, the first sliver of time after the Big Bang, space itself may have been frothing with microscopic black holes and wormholes. As these structures evaporated or collapsed, they could have released bursts of gamma rays that got locked into the fabric of expanding space-time. Unlike later astrophysical sources, these emissions wouldn't follow the usual rules of energy dissipation, potentially explaining why the background appears so unnaturally uniform across the sky. But verification remains a nightmare. Distinguishing between gamma rays from the universe's first microseconds and those produced yesterday by a distant blazar is like trying to isolate a single voice in a stadium roar. Current telescopes lack the spectral resolution to tease apart these ancient signals with certainty. That's why next-generation instruments like the Gamma Ray Large Area Space Telescope, or GLASS, are being designed specifically to hunt for these cosmological ghosts in the machine. What makes this mystery so critical is its connection to everything else. If we're truly seeing gamma rays from the universe's infancy, they could carry encoded details about inflation, quantum gravity, and even the nature of time itself. Each photon might be a message in a bottle from an era when the laws of physics as we know them were still being written. And that's what keeps astronomers digging, because in this cosmic fog might lie answers to questions we haven't even thought to ask yet. Buried in the flood of data from the Fermi Large Area Telescope are hundreds of gamma-ray sources that refuse to reveal their identity's cosmic signatures with no known counterparts in other wavelengths. These aren't just faint blips lost in the noise, they're bright, insistent signals screaming for attention. Yet when astronomers point optical, radio, or X-ray telescopes in their direction, they find nothing. No pulsar, no galaxy, no supernova remnant, just empty space where an explanation should be. This isn't a case of missing a few puzzle pieces. It's like stumbling upon an entire hidden chapter of the universe's high-energy playbook. What makes these unidentified Fermi-LAT sources so unnerving is their sheer variety. Some flicker erratically like blazars but lack the telltale jets or accretion disks. Others glow steadily, mimicking pulsars, yet no spinning neutron star lies at their hearts. A few even pulse with bizarre, irregular rhythms. No known celestial object behaves this way. It's as if the universe invented entirely new classes of gamma-ray emitters and forgot to include them in our textbooks. One particularly stubborn source, known as Fermi J0540-6960, sits tantalizingly close to the Large Magellanic Cloud, pulsing every 20 days like clockwork. But despite years of scrutiny, it has no visible host, no companion star, no plausible engine to power its rhythmic outbursts. the implications for the gamma-ray background are profound. If even a fraction of these mystery sources are common throughout the cosmos, too faint to spot individually but abundant enough to collectively shine, they could account for a significant chunk of the unresolved diffuse glow. Think of it like fireflies in a dark field. From a distance, their individual flashes blur into a uniform haze. But here's the twist: unlike known populations of faint sources, these objects don't match any expected distribution. They're not clustered along the galactic plane like pulsars, nor do they trace the web of galaxy clusters like blazars. Instead, they're scattered almost randomly, as if obeying a hidden logic we haven't deciphered yet. Some clues lurk in their energy spectra. A subset of the unidentified sources emit gamma rays predominantly in the 1 to 10 giga-electronvolt range, too soft for classic blazars, too hard for typical pulsars. This Goldilocks energy suggests unconventional particle acceleration mechanisms, perhaps from magnetars with freakishly strong magnetic fields or rogue black holes drifting between stars. Others show spectral bumps at specific energies, hinting at exotic particle decays or quantum gravity effects. One leading theory proposes that they could be dark matter subhalos, invisible clumps of shadowy particles annihilating in deep space. If true, each unidentified source might be a fingerprint of the universe's most elusive substance. The hunt for answers is pushing telescopes to their limits. Teams are now cross-referencing Fermi's catalog with infrared surveys, hoping to spot dust-shrouded objects invisible to optical scopes. Others are listening for faint radio whispers that might betray hidden neutron stars. But the most tantalizing breakthroughs come from multi-messenger astronomy, linking gamma-ray bursts to neutrino detections or gravitational waves. In 2017, a single unidentified Fermi source flared in tandem with a neutrino hitting Earth's detectors, raising hopes that these ghosts might finally be cornered through their interactions with other cosmic messengers. Every unidentified source is a potential Rosetta Stone for high-energy astrophysics. They could represent entirely new stellar evolution pathways, quantum anomalies in space-time, or even signs of advanced civilizations harnessing unthinkable energies. Until we crack their codes, they remain both a frustration and a gift, reminders that for all our maps and models, the universe still holds cards close to its chest. And as long as they glow unseen in Fermi's data, the gamma-ray background will keep one of its most provocative secrets. If the gamma-ray background were a perfectly smooth cosmic curtain, its mysteries might be easier to untangle. But the truth is far messier and far more revealing. Scattered across the sky are patches where the glow intensifies unexpectedly, like invisible mountain ranges rising from a flat plain. This unevenness, known as anisotropy, defies the assumption that gamma rays should distribute uniformly. Instead, it paints a portrait of hidden structures and unknown forces shaping the universe's highest energy light. Take the so-called Fermi haze near the Milky Way's core, a sprawling region where gamma rays concentrate with unsettling symmetry. Unlike random astrophysical noise, this haze aligns almost perfectly with the galaxy's disk, as if sculpted by the same magnetic fields that channel cosmic rays. Yet its energy spectrum is all wrong for conventional sources. The haze glows brightest at energies where dark matter particles are predicted to annihilate, sparking theories that we might be staring at the aftermath of countless invisible collisions. But proving it requires untangling the haze from overlapping emissions of pulsars and gas clouds, a task like isolating a whisper in a hurricane. Then there's the dipole anisotropy, a lopsided pattern where one hemisphere of the sky blazes slightly brighter than the other. This asymmetry points like a compass needle toward a patch of space near the constellation Hercules, but no known galaxy cluster or supervoid lies in that direction to explain the imbalance. Some suggest it could be the gravitational fingerprint of a neighboring supercluster, an immense wall of galaxies tugging on the cosmic web, while others wonder if we're seeing the shadow of our own Milky Way's motion through the universe, like a boat leaving a wake in high-energy light. Even stranger are the gamma-ray hotspots that coincide with vast filaments of dark matter threading between galaxies. These cosmic threads, revealed by gravitational lensing surveys, trace the skeleton of the universe, the scaffolding upon which ordinary matter assembles. When gamma rays cluster along these filaments, it hints that something, perhaps dark matter decay or shockwaves from primordial cosmic flows, is converting the universe's hidden architecture into light. The most provocative clue comes from the energy dependence of these anisotropies. Low-energy gamma rays clump differently than high-energy ones, suggesting multiple overlapping phenomena at work. Lower energy patches might trace the bones of galaxy clusters, while the highest energy blobs could mark the graves of ancient quasars, their billion-year-old light finally reaching us. Each layer of this cosmic palimpsest tells a different story, written in radiation we're only now learning to read. What makes the anisotropy problem so urgent is its potential to rewrite cosmology. If these patterns stem from dark matter, they'd offer the first tangible map of its distribution. If they reflect unknown large-scale structures, they could reveal how the universe organizes matter on scales beyond our current surveys. And if they're echoes of primordial physics like quantum fluctuations stretched across space-time during inflation, they might carry secrets from the universe's first trillionth of a second. Yet for all their promise, these gamma-ray unevennesses remain stubbornly cryptic, like staring at a rippled pond and trying to deduce the size and speed of every pebble that disturbed it. The task demands instruments of unprecedented precision. Future telescopes like the Cherenkov Telescope Array aim to dissect these patterns photon by photon, teasing apart the cosmic signals from the noise. Until then, the anisotropies stand as both a challenge and a beacon, proof that the gamma-ray background isn't just a fog, but a language waiting to be decoded. At the very edge of our gamma-ray detector's capability, where photons pack trillions of electron volts of energy, the universe throws another curveball, the TV excess. These aren't just high-energy gamma rays, they're the cosmic equivalent of bullets fired from an invisible gun, blasting through space with energies that rival the Large Hadron Collider's most powerful collisions. What baffles scientists isn't just their existence, but their sheer abundance. According to every mainstream model of particle acceleration in space, there simply shouldn't be this many ultra-high-energy photons flooding the cosmos. Yet they're there, glowing defiantly in our telescopes, daring us to explain them. The mystery deepens when you examine where these photons come from. Some originate near pulsars, those rapidly spinning neutron stars that act as natural particle accelerators. But here's the catch. Even the most powerful pulsar winds struggle to push particles to the energies required for TV gamma rays. It's like trying to launch a rocket to the moon with firecrackers. The math just doesn't add up. Other TV photons seem to stream from regions of seemingly empty space, with no visible engines capable of producing such extreme radiation. One striking example is the gamma rays detected from the direction of the Geminga pulsar's ancient tail, a structure thought to be too old and diffuse to still be cranking out such energetic particles. Then there's the puzzle of propagation. TV gamma rays shouldn't survive long journeys across interstellar space. They're so energetic that they inevitably collide with lower-energy starlight photons, annihilating into electron-positron pairs long before reaching Earth. Yet we detect them from sources thousands of light-years away, implying something perhaps undiscovered quantum effects or hidden magnetic fields is shielding them en route. Alternatively, the photons might not be traveling as far as we think, hinting at nearby accelerators we've somehow overlooked. Theories abound, each more tantalizing than the last. Some suggest microscopic black holes left over from the Big Bang could be evaporating in bursts of Hawking radiation, spewing out TV photons as they vanish. Others propose that dark matter particles millions of times heavier than protons might be decaying or colliding in distant halos, unleashing these gamma-ray bullets as byproducts. There's even a fringe idea that cosmic strings' hypothetical defects in spacetime could be vibrating like plucked guitar strings, releasing energy in concentrated spurts. What makes the TV excess so thrilling is its potential to rewrite physics. If conventional astrophysics can't explain it, we might be glimpsing cracks in the standard model, or even signs of extra dimensions crumpling at microscopic scales. Every unexplained photon is a clue, and with next-generation observatories like the Cherenkov telescope array coming online, we're closer than ever to cracking this high-energy enigma. One thing's certain, the universe's most violent particle accelerators are still keeping their secrets. Millisecond pulsars are the universe's silent speed demons, neutron stars spinning hundreds of times per second, their lighthouse-like beams flickering too quickly for most telescopes to catch. Unlike their younger, slower cousins, these ancient objects have been spun up to dizzying speeds by siphoning material from companion stars, their magnetic fields muted but their rotational energy relentless. And here's the twist, they might be hiding in plain sight, flooding the cosmos with gamma rays we've mistakenly chalked up to the background. At first glance, they seem like unlikely suspects. Millisecond pulsars are faint compared to the gamma-ray powerhouses we know: blazars, supernova remnants, or even regular pulsars with their towering magnetic fields. But what they lack in individual brightness, they might make up for in sheer numbers. Recent surveys suggest the Milky Way alone could harbor tens of thousands of these stealthy spinners, many too dim or distant to spot directly. Like fireflies in a foggy field, their combined glow could create a diffuse haze easily mistaken for something else. The smoking gun might lie in their unique gamma-ray fingerprints. Unlike younger pulsars, which emit most of their radiation at higher energies, millisecond pulsars tend to peak in the 1 to 10 giga-electronvolt range, precisely where a significant chunk of the unresolved background lingers. Even more telling, their emissions are remarkably steady, without the erratic flaring of blazars or the slowdowns typical of middle-aged pulsars. This consistency could explain why the gamma-ray background appears so smooth, as if painted by countless tiny brushes rather than a few broad strokes. Then there's the distribution puzzle. Gamma-ray telescopes have detected faint, unresolved emissions clustering near globular clusters, ancient stellar cities teeming with millisecond pulsars. These systems are so dense with stars that neutron stars frequently capture companions, spinning up over billions of years. If similar populations lurk undetected throughout galactic bulges and halos, their cumulative output might resolve a significant fraction of the missing background. But the plot thickens when you consider escapees. Some millisecond pulsars get kicked into interstellar space by violent encounters or supernova kicks, becoming lone wolves with no visible counterparts. Freed from the glare of their birth clusters, these orphans would be nearly invisible to optical telescopes, but their gamma rays would still bleed into the background, untraceable to any specific source. Simulations suggest there could be millions of these dark wanderers drifting through the galaxy, their faint pulses lost in the cosmic static. The real challenge is proving it. Identifying individual millisecond pulsars in gamma-ray data is like picking out a single voice in a stadium chant. Their rapid spins blur together in most surveys, requiring painstaking analysis of timing variations or lucky alignment with radio or X-ray detections. New machine learning techniques are helping sift through Fermi telescope data for these needle-in-a-haystack objects, but progress is slow. Every confirmed millisecond pulsar chips away at the background's mystery, yet the math still shows a gap. Even if we're missing thousands, they alone can't account for the full glow. Perhaps the most tantalizing possibility is that we're seeing a mix, millisecond pulsars contributing a baseline hum, while something even stranger, like dark matter or exotic quantum processes, fills in the rest. Or maybe these pulsars are more prolific gamma-ray producers than we've assumed, their emissions amplified by unseen magnetic fields or cosmic ray interactions. One thing's certain, until we can census these silent spinners, the gamma-ray background will keep its secrets close. What makes this mystery so compelling is its duality. Solve it, and we might not just account for missing light, we could uncover a hidden backbone of the universe, a shadow population of objects rewriting our understanding of stellar evolution. Every flicker in the data is a clue, and every unanswered question a reminder that sometimes the cosmos hides its greatest stories in the quietest places. Magnetic fields aren't just confined to galaxies or stars, they sprawl across the voids between galaxies, invisible rivers of force twisting through the cosmic web. These intergalactic fields are fiendishly weak, millions of times fainter than Earth's magnetic field, but their cumulative effect could be warping the gamma-ray background in ways we're only beginning to grasp. Picture a hall of mirrors where every reflection distorts the original image slightly. That's what might be happening to gamma rays as they traverse these magnetized highways, their paths bent just enough to scramble the clues to their origins. The trouble starts with how gamma rays interact with these fields. Unlike charged particles which spiral neatly along magnetic field lines, gamma rays are neutral. They shouldn't care about magnetism at all. But here's the catch: when a gamma ray collides with a lower energy photon, it can spawn an electron-positron pair, and these newly charged particles are sensitive to magnetic fields. They get whipped around, emitting secondary gamma rays in chaotic directions before annihilating back into photons. The result, a game of cosmic telephone where the original message, where the gamma ray came from, what energized it, gets garbled beyond recognition. This wouldn't matter if intergalactic fields were uniformly weak, but recent studies suggest they're patchy, clumping along the filaments of the cosmic web where dark matter and sparse gas congregate. Some regions might act like funnels, focusing gamma rays toward us, while others scatter them wildly. Simulations show these distortions could smear point sources into false diffuse glows or even create phantom anisotropies, patterns in the gamma ray sky that don't reflect real structures, just the magnetic funhouse they've passed through. The most mind-bending implication: we might be misreading the gamma ray background entirely. What looks like evidence for dark matter annihilation or primordial black holes could just be the echo of ordinary astrophysical sources, their signals mangled by magnetized voids. Take the Fermi Bubbles. Their crisp edges and symmetry might not trace an ancient explosion, but rather the contours of a magnetic barrier at the Milky Way's rim, sculpting gamma rays into unnatural shapes. Yet proving this is a nightmare. Intergalactic magnetic fields are too faint to measure directly, leaving astronomers to hunt for indirect signatures. One clue comes from gamma rays' polarization, a subtle alignment in their electric fields that can betray magnetic interference. A handful of observations hint at unexpected polarization in the background, but the data's too sparse to confirm. Another approach tracks gamma rays from distant blazars. If their photons arrive with skewed energy distributions or odd delays, it could signal turbulence in the magnetic fog they've traversed. The stakes are cosmic. If these fields are stronger or more tangled than assumed, they could cloak entire populations of gamma-ray sources, turning the background into a hall of mirrors where nothing is quite where or what it seems. Alternatively, if we can decode their distortions, we might unlock a new tool for mapping the universe's hidden scaffolding. After all, magnetic fields don't exist in isolation. They trace the flows of matter and energy we can't otherwise see. Every warped gamma ray might carry a hidden map of the cosmos's darkest reaches. For now, the intergalactic magnetic effect remains a ghost in the machine, a subtle, pervasive bias in our observations that could be skewing everything we think we know about high-energy astrophysics. Untangling it will require telescopes sensitive enough to spot the faintest whispers of polarization and supercomputers powerful enough to simulate the universe's magnetic labyrinth. Until then, the gamma-ray background's secrets might be hiding not just in the light we see, but in the invisible fields that shape its journey. The very first instance of the universe might be written in gamma rays we can't yet read. Cosmic inflation, that fleeting moment when the newborn cosmos expanded faster than light itself, should have left scars in the fabric of space-time. And some theorists believe those scars might still be glowing faintly in the gamma-ray background, like cosmic hieroglyphs waiting to be deciphered. Picture this: during inflation, quantum fluctuations smaller than atoms were stretched to astronomical scales, seeding the structures we see today: galaxies, clusters, the cosmic web. If those same fluctuations also generated primordial gravitational waves, they could have shaken the universe's electromagnetic field like a drumhead, producing bursts of high-energy photons. Over 13 billion years, those photons would have cooled and redshifted, but their descendants might still linger in the gamma-ray fog we observe. It's a long shot, but the math suggests these relics could carry distinct spectral signatures, subtle peaks or troughs in the background's energy distribution that no astrophysical process can mimic. The challenge is separating this signal from the noise. Inflation-era gamma rays would be hopelessly diluted, their fingerprints blurred by eons of cosmic expansion and drowned out by younger, brighter sources. But there's a tantalizing clue. Certain models predict these primordial photons should correlate with the universe's large-scale structure, clustering where matter is densest. If we could map the gamma-ray background against the cosmic web's filaments and voids, we might spot unnatural patterns, regions where the glow is slightly too bright or too dim, betraying an ancient hand in its making. Some researchers are hunting for this connection in the data. They've identified faint anisotropies in the gamma-ray sky that align suspiciously well with the distribution of galaxy superclusters, a potential echo of inflation's quantum ripples. Others are searching for circular polarization, a twisted quality in the light that could only arise from universe-shaking gravitational waves. So far, the evidence is circumstantial at best, but next-generation telescopes like the Gamma-Ray Large Area Space Telescope, or GLASS, could finally have the sensitivity to tease out these whispers from the cosmic static. What makes this idea so revolutionary isn't just its audacity, it's the stakes. If the gamma-ray background holds even a trace of inflation's fingerprint, it would be the first direct proof of that epoch, a window into physics at energies a trillion times beyond what particle colliders can reach. We'd glimpse the universe not just as it was moments after the Big Bang, but before the bang as we know it, when the laws of physics themselves were being written. Of course, alternative explanations abound. The same anomalies could stem from undiscovered particle interactions, dark matter decay, or even systematic errors in our observations. But that's the beauty of this mystery. Whether inflation's signature is there or not, the search is forcing us to ask deeper questions about how the universe began and what stories its oldest light might still be telling. One thing's certain: if these gamma rays really are cosmic fossils, they're the most valuable ones we've ever hunted. Galaxy clusters should be gamma-ray factories, these colossal cities of galaxies, bound together by gravity and swimming in hot gas, are natural particle accelerators on a cosmic scale. When cosmic rays zip through their magnetized gas clouds, collisions should produce gamma rays in abundance, painting these clusters as bright beacons in the high-energy sky. Yet when astronomers point their telescopes toward these massive structures, they come up shockingly empty-handed. The gamma-ray glow from clusters is a mere whisper compared to predictions, leaving scientists scrambling to figure out where the light went. Take the Perseus cluster, one of the most massive known assemblies of galaxies. Packed with enough hot gas to forge stars for eons and home to a supermassive black hole pumping out energy, it should shine brilliantly in gamma rays. Instead, the signal is so faint it barely registers above the background noise. It's like expecting a spotlight and finding a single flickering candle. This mismatch isn't unique. Study after study finds the same deficit across dozens of clusters, as if some unseen hand is turning down the universe's gamma-ray dial. One leading theory blames the cluster's magnetic fields. These tangled webs of force might be trapping cosmic rays within the gas, preventing them from escaping and producing gamma rays where we can see them. Imagine a high-energy particle trying to exit a maze. It spirals endlessly along magnetic lines, losing energy until it can no longer ignite the gamma-ray reactions we expect. If this is true, clusters could still be producing gamma rays, but they're effectively trapped inside, their light muffled by magnetic insulation. Another possibility is that the gamma rays are being produced, just not where we're looking. Simulations suggest that shocks from galaxy collisions or outbursts from central black holes might push cosmic rays into the vast, sparsely populated outskirts of clusters. Out there, far from the dense gas clouds, interactions are rarer, leading to fewer gamma rays overall. It's like expecting fireworks in a packed stadium but finding them fizzling out in the empty parking lot instead. Then there's the dark matter factor. Many models assume dark matter annihilations in cluster cores should contribute extra gamma rays, adding to the expected signal. If these annihilations aren't happening, or if dark matter behaves differently than predicted, it could explain the shortfall. Yet when researchers compare gamma-ray observations with dark matter maps, the puzzle only deepens. Some clusters with the densest dark matter halos show no gamma-ray excess at all, while others with minimal dark matter somehow emit more than expected. It's as if the rules change from cluster to cluster, defying any single explanation. The most unsettling implication: our understanding of particle acceleration in these environments might be fundamentally flawed. Galaxy clusters are thought to ramp up cosmic rays to extreme energies through shockwaves and turbulence, but if those mechanisms are less efficient than assumed, the gamma-ray shortfall starts to make sense. Perhaps the particles lose energy too quickly, or maybe the cluster's magnetic fields are redirecting them in ways we haven't accounted for. Every missing gamma ray is a clue, hinting at hidden physics playing out in these dense cosmic metropolises. Until we solve this riddle, galaxy clusters remain cosmic paradoxes, powerhouses of energy that stubbornly refuse to shine as brightly as they should. Whether the answer lies in magnetic prisons, elusive dark matter, or something stranger still, one thing's clear: the universe's largest structures are keeping secrets, and their silence speaks volumes. When a star wanders too close to a supermassive black hole, the results are both spectacular and gruesome. Gravity's tidal forces stretch the star like taffy until it snaps apart in a cataclysmic flare known as a tidal disruption event. For months, the shredded stellar debris spirals into the black hole's maw, glowing brilliantly across the electromagnetic spectrum. These cosmic feasts should be gamma-ray gold mines, unleashing jets of high-energy particles as the black hole devours its meal. Yet when astronomers search for their fingerprints in the gamma-ray background, the numbers don't add up. These violent encounters are either far rarer than predicted, or hiding something unexpected about how black holes process matter. The disconnect starts with basic physics. Simulations suggest that during a tidal disruption event, up to half a star's mass gets funneled into relativistic jets as it's torn apart, accelerating particles to energies that ought to produce copious gamma rays. Observations of individual events seem to confirm this, like the infamous Assassin 14 lie, whose flare-up was caught spewing X-rays and gamma rays after a black hole 20 times the sun's mass shredded a passing star. Multiply that by the thousands of supermassive black holes lurking in galaxies across the cosmos, and tidal disruptions should collectively contribute a noticeable fraction of the diffuse gamma-ray glow. Instead, surveys find their total impact is barely a rounding error in the background's budget. One possibility is that most tidal disruption events are simply shy. Not every black hole launches visible jets when it dines. Some may swallow stars quietly, like a predator consuming prey without a struggle. Magnetic field geometry plays a role. If the black hole's spin and the star's orbit are misaligned, the resulting jets could be weak or unfocused, scattering their energy harmlessly into space. Other disruptions might occur in galaxies so dust-choked that their gamma rays never escape. It's like trying to count campfires during a sandstorm. The glow is there but obscured. Then there's the timing problem. Tidal disruptions are fleeting by cosmic standards, with jets that flare brightly for months before fading into oblivion. The gamma-ray background, by contrast, is steady as a metronome, a smooth hum suggesting continuous, widespread emission rather than sporadic fireworks. Unless these events are happening far more frequently than we've observed, they can't explain the background's persistence. Some theorists propose a hidden population of repeating disruptions, where black holes nibble at stars over centuries instead of gulping them whole, but evidence for such drawn-out feasts remains scarce. The real twist comes from events that shouldn't produce gamma rays, yet do. Normally, only the most massive black holes, those weighing millions of suns, are thought capable of powering luminous jets during stellar disruptions. But in 2019, astronomers spotted a tiny black hole, just 10 solar masses, generating gamma rays as it shredded a star. If petite black holes are getting in on the act, their sheer numbers across the universe might collectively contribute more to the background than anyone guessed. What's at stake isn't just a tally of cosmic carnage. If tidal disruptions are secretly more prolific or efficient gamma-ray producers than we've accounted for, they could help bridge the gap between known sources and the unresolved background. Alternatively, their absence might hint at gaps in our understanding of black hole astrophysics, like how jets form or why some disruptions go dark. Every unobserved flare is a clue, and every detected one a potential Rosetta Stone for decoding the universe's hidden light. For now, tidal disruption events remain wild cards in the gamma-ray deck, capable of brilliance, but reluctant to show their hand. Unlocking their secrets will require telescopes that catch them in the act, from the first fatal stretch of a star to the last flicker of its demise. Until then, these cosmic shredders linger in the shadows, their full role in the high-energy universe still waiting to be told. Some of the universe's greatest secrets might be hidden not in the vastness of space, but in the tiniest wrinkles of reality itself. When we zoom in beyond atoms, beyond subatomic particles, to scales so small they defy comprehension, the very fabric of space-time may be fizzing with quantum activity, and this microscopic turbulence could be imprinted on the gamma-ray background in ways we're only beginning to imagine. At these unimaginably small scales, gravity stops playing by Newton's or Einstein's rules. Instead, it becomes subject to the same quantum weirdness that governs particles, fluctuating, probabilistic, and potentially intertwined with extra dimensions we can't perceive. Theorists suggest that if space-time has a quantum foam structure where microscopic black holes blink in and out of existence, their evaporations could release faint bursts of gamma rays that accumulate into a diffuse glow across the cosmos. It's like listening for the static between radio stations and discovering it's actually the crackle of space itself. The most tantalizing possibility involves extra dimensions. Some quantum gravity models propose that our universe has more than the 3 spatial dimensions we experience, hidden dimensions curled up so tightly we'd never notice them in daily life. But when gamma rays traverse these folded dimensions, their energy might subtly shift, creating patterns in the background that no conventional astrophysics can explain. Imagine throwing a ball into a corridor you didn't know existed. Its trajectory would change in ways that seem impossible unless you account for the hidden path. Gamma rays might be doing the same thing on cosmic scales. Then there's the holographic principle, a radical idea suggesting our 3-dimensional universe could be a projection from a 2-dimensional boundary, like a cosmic version of a hologram sticker. If true, quantum interactions at this fundamental level might leave faint gamma-ray signatures, perhaps as unexpected correlations in the background's fluctuations or as anomalies in how gamma rays propagate across vast distances. Teams analyzing Fermi telescope data have reported statistical oddities that could hint at such effects, though the evidence remains controversial. What makes these theories so electrifying is their testability. Certain quantum gravity models predict very specific distortions in the gamma-ray spectrum, tiny bumps or dips at precise energies where space-time's granularity becomes apparent. Others forecast that gamma rays from distant sources should arrive slightly out of order if they've taken shortcuts through higher dimensions. While current instruments lack the precision to confirm these effects, next-generation observatories like the Cherenkov Telescope Array are being designed specifically to hunt for these quantum fingerprints. The implications are staggering. If the gamma-ray background carries even a whisper of quantum gravity's influence, it would be our first empirical window into physics at the Planck scale, energies a quadrillion times beyond what particle colliders can reach. We might finally understand how gravity marries with quantum mechanics, or whether extra dimensions truly exist. Or we could discover something entirely unforeseen, rewriting not just astrophysics but the fundamental rules of reality. For now, these ideas remain at the frontier of speculation, beautiful mathematical possibilities waiting for experimental validation. But that's the thrill of the gamma-ray background. It's not just a cosmic artifact, but a potential Rosetta Stone for decoding the universe's deepest layers. Every photon we can't explain with known physics might be carrying a message from realms beyond space and time as we know them. And if we learn to read those messages, the universe might finally reveal how it truly works at the most fundamental level. Dwarf galaxies are the shy, quiet neighbors of the cosmic community, small, dim, and easy to overlook. Yet these unassuming structures might be hiding a secret. They could be silently flooding the universe with gamma rays, contributing far more to the mysterious background glow than anyone ever suspected. The idea is deceptively simple. If the cosmos is teeming with countless faint, undiscovered dwarf galaxies, each too small to spot individually but collectively vast in number, their combined gamma-ray emissions might blend into the smooth, all-sky haze we observe. It's like standing in a field at night, surrounded by thousands of distant fireflies. No single insect's glow stands out, but together they cast an unmistakable luminescence. The math is compelling. Dwarf galaxies, especially those rich in dark matter, should be prime candidates for gamma-ray production. Their gravitational wells trap cosmic rays, which then collide with gas and dust, sparking high-energy light as a byproduct. Some dwarfs, like the famous Segway one, already show faint gamma-ray excesses that hint at dark matter annihilations within their cores. But here's the catch. Known dwarfs are too few and too dim to explain more than a sliver of the background. The real game-changer would be a hidden population galaxies so small and dark they've slipped through every observational net. Simulations suggest these ghosts might be everywhere. Cosmological models predict that the universe should contain hundreds, perhaps thousands, of ultra-faint dwarfs orbiting the Milky Way alone. Most would be virtually invisible, their stars scattered so thinly they'd barely register against the night sky. Their dark matter halos, however, could be seething with particle collisions, each one a miniature gamma-ray factory. If even a fraction of these predicted dwarfs exist, their cumulative output might resolve a significant chunk of the unresolved background. The challenge proving they're out there. Recent advances in observational techniques are starting to lift the veil. Telescopes like the Vera-C, Rubin Observatory, with its unprecedented ability to scan vast swaths of sky for the faintest stellar clumps, could soon uncover this hidden demographic. Already, astronomers have spotted a handful of dark galaxies, objects with almost no stars but plenty of dark matter, using subtle gravitational lensing effects. If these systems are leaking gamma rays, they'd be the perfect stealth contributors to the background. their emissions untraceable to any visible source. Yet the theory isn't without wrinkles. Even if undetected dwarfs abound, their gamma rays would still need to escape their host galaxies, no sure bet in such dense, gas-rich environments. Some models suggest these photons might be absorbed and re-emitted at lower energies, blurring their origins beyond recognition. Others argue that without frequent supernova to drive particle acceleration, dwarfs might lack the machinery to produce gamma rays in the first place. The most tantalizing clue lies in the background's anisotropy, those faint, patchy irregularities we discussed earlier. Some of these fluctuations align suspiciously well with predicted distributions of missing dwarfs, as if the gamma-ray fog is subtly thicker where invisible galaxies should lurk. It's circumstantial evidence, but the kind that keeps astronomers scanning the data for that one definitive correlation. What's at stake isn't just an accounting exercise. If the missing dwarf hypothesis holds, it would rewrite our understanding of galaxy formation, dark matter physics, and the cosmic census all at once. These galaxies could be the universe's most numerous structures, their collective glow a fingerprint of the vast, unseen architecture shaping everything we see. And until we find them or rule them out, they remain both a tantalizing solution and a haunting reminder of how much we have yet to discover. Neutrinos are the universe's most elusive particles, tiny, nearly massless ghosts that slip through entire planets as if they weren't there. Born in the hearts of stars, black holes, and violent cosmic explosions, these high-energy messengers should have a lot in common with gamma rays, their flashier, more detectable cousins. Both are produced in some of the universe's most extreme environments, racing across space as fingerprints of the same catastrophic events. Yet when astronomers compare the arrival directions of gamma rays and neutrinos, the results are anything but straightforward. Sometimes they match up perfectly, like twin signals from a distant blazar. Other times, gamma rays flood in without a single neutrino counterpart, or stranger still, neutrinos arrive with no gamma rays in sight. This cosmic mismatch isn't just a quirk of observation. It's a fundamental puzzle about how the universe packages and delivers its highest energy particles. Take the case of the blazar TXS 0506 plus 056, a supermassive black hole 3.7 billion light-years away. In 2017, it erupted in a flare of gamma rays so powerful it lit up detectors across the globe. At nearly the same moment, the Ice Cube Neutrino Observatory at the South Pole captured a single, ultra-high-energy neutrino, and backtracking its trajectory pointed almost directly at the blazar. This was the first time scientists had traced a neutrino to an astrophysical source, and it seemed to confirm that blazars were neutrino factories, accelerating particles to unfathomable speeds. But here's the twist: when researchers combed through decades of gamma-ray and neutrino data, expecting a flood of similar matches, they found barely a handful. For every neutrino linked to a gamma-ray source, there were thousands of gamma-ray flares with no neutrinos at all, and a growing number of orphan neutrinos arriving from seemingly empty patches of sky. This disconnect forces us to rethink how particle acceleration really works in the cosmos. Gamma rays and neutrinos are both byproducts of violent particle collisions, but they're born from different ingredients. Gamma rays often come from electrons smashing into photons, while neutrinos require protons or heavier atomic nuclei slamming into gas or dust. If a cosmic accelerator favors electrons over protons, or if its magnetic fields filter out certain particles, it might produce gamma rays without neutrinos or vice versa. It's like expecting a bakery to always sell both croissants and baguettes, only to find some ovens only bake one or the other for reasons we don't yet grasp. Even stranger are the neutrinos that arrive with no gamma-ray escort. These lonely particles might be coming from sources so shrouded in dust or gas that their gamma rays get absorbed before escaping. Imagine a car crash happening inside a tunnel. You might hear the noise, the neutrino, but see no flash of light, the gamma ray. Alternatively, they could be born in environments where gamma rays are suppressed entirely, like the cores of dense galaxy clusters or the chaotic aftermath of a neutron star merger. Some theorists even suggest these orphan neutrinos might be the death cries of dark matter particles, annihilating in the void without emitting the light we expect. The most tantalizing possibility involves cosmic censorship, regions of spacetime so warped by gravity that they hide their gamma rays behind event horizons or magnetic shields. If a black hole's jet is pointed just slightly away from Earth, its gamma rays might miss us entirely, while neutrinos, indifferent to direction, barrel straight through. This could explain why we're missing so many expected neutrino-gamma pairings, and why the cosmic ledger of high-energy particles refuses to balance. What's clear is that every mismatch between gamma rays and neutrinos isn't just noise, it's a clue. The universe is selective about how it reveals its secrets, and these silent, ghostly particles might be holding keys to doors we didn't even know were locked. As detectors like IceCube and future neutrino observatories grow more sensitive, we're not just solving a puzzle, we're learning to listen to the cosmos in a whole new wavelength, one that whispers where gamma rays shout and reveals what light alone can never show. The universe is supposed to be predictable, at least on cosmic timescales. Stars burn for billions of years, galaxies rotate with clockwork precision, and even violent events like supernova follow well-understood patterns of rise and decay. But the gamma-ray background refuses to play by these rules. Unlike the steady glow of starlight or the microwave hum of the Big Bang's afterglow, this high-energy fog might be shifting and flickering in ways we're only beginning to detect. If true, it would rewrite our assumptions about where these photons come from and what's really happening in the hidden corners of the cosmos. For decades, astronomers assumed the gamma-ray background was as unchanging as the constellations, a permanent fixture woven into the fabric of space. Early telescopes lacked the sensitivity to spot subtle variations, and with no obvious culprit for time-sensitive emissions, the idea of a dynamic background seemed far-fetched. That changed when the Fermi Gamma-Ray Space Telescope began its marathon scan of the sky, logging photon counts year after year. Hidden in its ocean of data were whispers of something strange. Certain patches of the gamma-ray sky appeared brighter in some years and dimmer in others, as if an invisible hand were turning a cosmic dimmer switch. The pattern defies easy explanation. Known gamma-ray sources like blazars or pulsars fluctuate wildly, but their individual flickering should average out across the vastness of space, leaving the background smooth and steady. Instead, we're seeing slow, synchronized waves of change regions thousands of light-years wide, brightening and fading in unison. One provocative theory suggests these variations might trace back to dark matter, whose particles could be annihilating in dense clumps scattered throughout the galaxy. If those clumps orbit the Milky Way's core at different rates, their gamma-ray output might rise and fall over decades, creating a subtle pulse hidden in the background's glow. Then there's the intergalactic lensing hypothesis. Massive structures like galaxy clusters warp spacetime around them, bending light like a funhouse mirror. If a distant gamma-ray source passes behind one of these gravitational lenses, its light could be magnified temporarily, creating the illusion of a brightening background in that patch of sky. The catch: these lensing events should be random and short-lived, not the gradual, recurring shifts we're detecting. Unless entire filaments of the cosmic web are vibrating like plucked strings, warping light in rhythmic cycles we've yet to model. The most unsettling possibility is that we're seeing the wake of something vast moving through intergalactic space, a supermassive black hole ejected from its galaxy, perhaps, or a dark matter avalanche cascading through unseen dimensions. These titanic events could stir the cosmic pot, accelerating particles across galactic distances and imprinting slow-motion ripples on the gamma-ray sky. Proving any of this will require patience. Gamma-ray astronomy is still young, and we've barely sampled a cosmic blink's worth of data. Future telescopes might catch the background mid-shift, revealing whether these variations are cyclical or chaotic, local or universe-wide. But one thing's certain, if the gamma-ray fog is truly alive with change, it's not just a backdrop, it's a dynamic character in the universe's story, one we're only starting to understand. Stretching across billions of light-years like the veins of the universe, the cosmic web is the largest structure we know, a labyrinth of dark matter filaments connecting galaxies in a delicate, invisible lattice. While we've mapped its shadowy outline through gravity's pull, one question lingers: could these vast intergalactic highways be humming with gamma rays, quietly feeding the mysterious background glow? The idea isn't as far-fetched as it seems. Within these filaments, particles accelerated to extreme energies might collide, sparking gamma-ray whispers we've yet to decode. Picture a filament, a river of gas and dark matter so sparse it makes Earth's atmosphere seem dense by comparison. Yet across millions of light-years, even these wispy corridors accumulate staggering energy. Cosmic rays, trapped by magnetic fields woven through the web, could ricochet for eons, occasionally smashing into stray protons or photons with enough force to birth gamma rays. Simulations suggest these interactions should be rare, but when stretched across the universe's entire scaffolding, their collective output might leave a detectable imprint. The challenge: disentangling this signal from the cacophony of galaxies, black holes, and other known gamma-ray sources. Some astronomers hunt for telltale patterns: gamma rays clustered along the web's predicted threads, like dew clinging to a spider's silk. A faint but tantalizing hint emerged in 2018 when researchers noticed an alignment between unresolved gamma-ray blobs and the positions of distant galaxy superclusters. The correlation was subtle, like catching a whisper in a storm, but it raised a provocative possibility. The cosmic web might not just structure matter, it could be glowing ever so faintly in the highest energy light. The real enigma lies in the mechanisms. If the web's gamma rays come from cosmic ray collisions, why don't galaxy clusters, denser knots in the web, shine far brighter? One theory invokes invisible accelerators, shock waves from ancient galaxy collisions or dark matter annihilations pumping particles to extreme speeds across filamentary highways. Another proposes that the web's magnetic fields, though faint, are vast enough to focus gamma rays into coherent streams, creating illusions of point sources where none truly exist. Then there's the dark matter question. If filaments are denser in dark matter than once thought, their particles might annihilate or decay at rates just high enough to contribute to the background. Intriguingly, certain models predict gamma-ray spectra from dark matter would peak at energies where the background's anisotropy is most pronounced, as if the universe is leaving breadcrumbs pointing to its hidden architecture. For now, the cosmic web's gamma-ray signature remains a ghost in the data, too faint to confirm, too compelling to ignore. Future telescopes, like the Cherenkov Telescope Array, might finally catch this elusive light, mapping the universe's skeleton not through gravity's indirect tug, but by the high-energy glow it casts. Until then, the filaments linger as both map and mystery, their secrets written in photons we're still learning to see. The greatest breakthroughs in gamma-ray astronomy might still be waiting in the wings, poised to unfold as a new generation of telescopes and detectors takes to the skies. Imagine instruments 10 times more sensitive than Fermi, telescopes capable of resolving the faintest whispers of high-energy light, and satellites designed to trace gamma rays back to their origins with pinpoint precision. This isn't just wishful thinking, it's the near future. Projects like the Cherenkov Telescope Array, or CTA, are set to revolutionize our view of the gamma-ray sky. Unlike traditional space telescopes, the CTA will consist of over 100 ground-based dishes spread across 2 hemispheres, working in concert to catch the fleeting flashes of blue light produced when gamma rays strike Earth's atmosphere. With resolution sharp enough to distinguish individual gamma-ray sources in crowded regions like the galactic center, it could finally unmask hidden populations of pulsars, dwarfs, or even dark matter clumps currently blending into the background's fog. Then there's the Gamma-Ray Large Area Space Telescope, or GLASS, a proposed mission designed to pick up where Fermi leaves off. While Fermi brought the gamma-ray sky into focus, GLASS would peer deeper, capturing photons at energies so high they currently slip through our observational cracks. Its detectors could spot spectral bumps or dips that betray quantum gravity effects or decaying dark matter, subtle fingerprints invisible to current instruments. GLASS might even catch gamma rays from the universe's first microseconds, relics of inflation or primordial black holes that have cooled over billions of years but still carry echoes of their birth. But the real game-changer could come from multi-messenger astronomy, the art of pairing gamma-ray data with signals from gravitational waves, neutrinos, and cosmic rays. Upcoming observatories like the Einstein Telescope, a next-gen gravitational wave detector, or the expanded Ice Cube Neutrino Observatory will let scientists triangulate gamma-ray bursts with unprecedented accuracy. Picture catching a gamma-ray flare, a neutrino pulse, and a gravitational wave ripple all from the same cosmic collision. Such events could reveal whether gamma rays are escaping distorted by magnetic fields or if they're being shadowed by unseen structures in the cosmic web. And let's not forget the wildcards experiments probing fundamental physics that might indirectly solve gamma-ray puzzles. Particle colliders like the Future Circular Collider, slated to dwarf the Large Hadron Collider, could manufacture dark matter candidates in the lab, testing whether their predicted gamma-ray signatures match the background's anomalies. Quantum sensors designed to measure spacetime's tiniest fluctuations might uncover whether gamma rays are taking shortcuts through extra dimensions. Even AI-driven sky surveys could uncover patterns in the background's anisotropies too subtle for human analysts to spot. What makes this era so thrilling isn't just the technology, it's the sheer breadth of possibilities. With each new instrument, we're not just building better tools, we're rewriting the rules of discovery. The gamma-ray background, once a frustrating enigma, could become a Rosetta Stone for everything from dark matter to the birth of spacetime itself. The answers are out there, etched in light we're finally learning to read. And when they come, they won't just solve mysteries, they'll reveal a universe far stranger and more magnificent than we've dared to imagine. From the eerie uniformity of the diffuse gamma-ray background to the explosive enigma of tidal disruption events, we've journeyed through 25 of the cosmos' most baffling puzzles, each one a reminder of how much we've yet to uncover. These mysteries aren't just gaps in our knowledge, they're portals to entirely new physics, hidden realms of the universe that defy everything we think we understand. The gamma-ray sky is more than a map of high-energy light. It's a mirror reflecting our own ignorance, showing us just how much lies beyond the edge of our current charts. Consider the contradictions we've encountered. Blazars that should dominate the background but don't, galaxy clusters that glow far too faintly, and dark matter that whispers but refuses to shout. We've traced the faint echoes of inflation's birth cries and the phantom fingerprints of quantum gravity, only to find the evidence slipping through our fingers like cosmic smoke. The Fermi Bubbles loom over us, colossal and unexplained, while unidentified sources flicker in the data like Morse code from an unknown sender. And through it all, the background hums steady, unchanging, and utterly indifferent to our confusion. Yet this isn't a story of failure. Every unanswered question is an invitation, a challenge to look deeper, think bigger, and question the assumptions that anchor our models. The universe doesn't owe us clarity. It rewards curiosity with layers of complexity, each mystery peeling back to reveal another. What if the anomalies in the gamma-ray background aren't problems to solve, but clues to a grander narrative? Maybe dark matter isn't just missing mass, but a key player in high-energy physics. Maybe the cosmic web isn't just scaffolding but an active participant in particle acceleration. Or maybe, just maybe, the answers lie in phenomena so alien we haven't even conceived them yet. That's the thrill of this hunt. Gamma-ray astronomy isn't just about cataloging photons, it's about decoding the universe's most energetic language. Every telescope we build, every algorithm we train, and every theory we test brings us closer to truths that could redefine reality itself, so stay curious. The next breakthrough might come from a lone researcher staring at a data glitch, a chance observation in a neglected wavelength, or even, who knows, a viewer like you inspired to ask the right question at the right time. Because the universe's greatest secrets aren't hiding, they're glowing, faint but insistent, waiting for someone to finally notice.